Okay, our next talk is by Sara Tukachinsky, and she will talk about spectral numbers of quantum cohomologies.
Yes. So thank you for having me. I'm very happy to be a good student. I'm also very happy to be in a real class. I want to talk today about a project that's not so much about what I did in the past as it is about what I hope to do. One of the few things I hope to be doing this year. And let me start by explaining the universe I live in, which is a symplectic one. So my manifold is a smooth symplectic manifold, compact, no boundary. Symplectic means it's equipped with a two-dimensional notion of volume, and it comes with an almost complex structure, which just, I see the powers on my board here. That's unfortunate. Let's hope it gets better. I don't know. Sorry, I should have checked with this before starting. So, almost complex structure. So think complex manifolds, these are good for intuition purposes. Pick your favorite Kähler manifold, which will be both complex and symplectic in a compatible way. And my personal favorite is probably CPM, but that's because I'm boring. And an important warning I should clarify is that I am going to be omitting a lot of very important details. And the reason is because, well, one of the reasons is because I have 15 minutes, but the other reason is because the purpose of this presentation for today is just to give a general picture of what's going on. There was a lot of heavy analysis going on in the background. I'm not going to go into any of that. So take today's talk as hand waving, that's all it really is. And now the next thing I want to do is to justify the plural I had in the title. So it was spectral numbers and quantum cohomologies. So the numbers may be plural, it's not surprising to anyone, but cohomologies may be plural. Yeah. What are we going to do? Should we?
Don't worry, we can figure it out.
Yeah. Well, that's true. You're probably the most intelligent audience I could hope for, but that's unfortunate. I do apologize for the glitch. Yeah, so those funky arrows are supposed to be powered, and so the star is supposed to be on power, and so on and so forth. It will unfortunately happen in the future as well. Let's hope stubbing these things will work better. Yeah, close, quantum cohomology. So that's the vanilla flavor, is if all we have is the structure I mentioned in the previous slide. So symplectic structure and almost complex structure, that's the kind of cohomology you have, and that's the kind of cohomology I will spend most of the time today talking about. Because it will be easiest for me to give a picture. If in addition to that, you also, yeah, and the down arrow is supposed to be a subindex, I'm sorry. If in addition to that, we fix a submanifold, that's a Lagrangian submanifold just means it's half a dimension, and it plays nice with the symplectic structure, then we get two other types of cohomology that I will briefly mention. But not really go into details about. So let me zoom in on this closed case, the quantum cohomology. Beautiful. As a module, you all know. Okay, okay, as a module, you all know exactly what this is. It's just your usual cohomology. And I use the DeGrom model because it's awesome, but you are welcome to think, again, we're only hand waving here, so think symplectic, think, sorry, singular, homology, cohomology, it's a closed manifold, they're dual. Pseudocycles, simplicial complexes, whatever floats your boat. What makes it quantum is the ring structure, so the product. Okay, the product. So how do we write down the product? We take two classes and we can decompose the product by a basis. And okay, I'm not sure that this is readable at this point. Is this readable at all?
Well, everything except that funny thing in front of the N.
In front of the N. I honestly not even sure what it was supposed to be. Yeah. I'm so sorry. Okay, so there's no art for not using Beamer. Okay. We decompose it by a basis. The coefficients of this basis are some numbers that are determined by count of holomorphic spheres that pass through those things. So let me make a picture. And of course the colors don't work. Okay. I got you. Focus. Yes, picture. We started with two representatives of the cohomology classes. So this is a very schematic picture because why not? I'm just taking, say, two submanifolds that represent the classes of A and B. And then I ask myself, well, what spheres intersect these two representatives? And then the number A, B, C will count those that intersect those two and also C. So another way of thinking about it is, say, let's take all the spheres that intersect A and B, see where else the sphere can go, and the geometric locus of wherever this sphere can also go is going to trace a representative of the quantum product. And I know it looks bizarre, and not only because of the glitches in the presentation, but it genuinely looks bizarre. Hopefully, it may look a little bit less bizarre if we focus on a special case of constant spheres. I said the sphere is supposed to be holomorphic. A special case of being holomorphic is being constant. So the image of a sphere is going to be just a point. Yeah, this picture is even more schematic. But the idea here still is that it's supposed to be thinking about a sphere with two submanifolds intersecting it. And if my sphere is a constant one, then for them to intersect the sphere just means that they intersect each other. And if I take a third point on the same sphere, well, where can that third point go? It can only go to that very intersection point. So if I just take into account constant spheres, I recover the usual intersection product from homology, which is what graduates the cup product in cohomology, or the wedge product on the Durand cohomology. So that's one you should be hopefully familiar with on some level. And then the quantum product just says, well, instead of asking for things to intersect on the nose, we ask for them to intersect up to a sphere. Yeah. So now that we're all experts in quantum cohomology and reading weird presentations, let's move to the second part of the title, which was spectral numbers. And I will try to describe these numbers in two steps. The first step would be to forget everything I told you so far. Well, except that I still work with a symplectic manifold. But the objects I want to consider now in the symplectic manifold are loops. I will take the space of loops that are contractible. So objects in my space here are loops with candidate fillings. Another piece of information that I'm going to add to the story is a function. It's time dependent, but it's cyclic in the time coordinate. Hamiltonian is just a fancy adjective that says it plays nice with the symplectic structure. You can forget about it. A function. And now this function sort of, it defines a functional on that space of loops. It's a very particular functional that we use in practice. Okay, I think the funky square just means that we move from the integral with its boundaries to wherever the integrand is. So the integral is supposed to be from 0 to 1, because that's the coordinate in S1. I think of it as R1z, where I plug the loop in F at time t, and the integral over U of the 2 form omega, which is a symplectic form. Yeah. Okay, but you don't have to worry about the precise expression. Point is, there is an associated functional on this space of loops. And then the idea here is going to be play Morse theory with this function. So we construct a chain complex where the chain complex is generated by critical points of this functional, and there is a way to define a differential so that we get indeed a chain complex. So therefore a cohomology, and that cohomology comes with a product with a fancy name pair of Banks product, because that's what it looks like. So what would be the product of two loops? Again, we might want to write it as a linear combination of some vector bases where the coefficient is again going to be a number, but instead of counting spheres that pass through stuff, we're going to count a different type of curve that's maybe more relevant to the story, namely this curve. You can think of it as a sphere minus 3 points, or you can think of it as a disk minus 2 points, or a cylinder minus 1 point, or your little pair of pants, which is the official name for this kind of curve. So we take a pair of pants that has legs, that's where the legs sort of go to those given loops, and we see where the third leg goes. That gives you the output of the product. So maybe the flavor of this product looks familiar, hopefully, because it kind of sounds similar to what we did before. Maybe it will look even more familiar if we focus on the special case where the function is a constant one. Because it is a fact of life that when the function is constant, then the critical points of that functional AF are also constant loops. And in which case a pair of pants between them looks just like a, well, a somewhat squished, but still a sphere. So all it is a sphere that takes 2 inputs and sees where the third point can go. Maybe it will not be entirely surprising if I tell you that indeed the cohomology of this weird, complex loops is in fact isomorphic. It recovers as a ring, not just as a module, but as a ring. It recovers the quantum cohomology I described before. So that was step 1. Step 1 was to take our quantum cohomology that we already know and identify it with a different type of complex. Why would I want to do that? Because this other complex comes with extra data. It comes with this F, or the AF as the case may be. So therefore I can define, okay, one of the indices is lambda, the other one is star. You feel free to place one of them up and the other down. Star is because it's a complex, lambda is because there's a filtration. You take only those, generate only those critical points where the value of the functional is smaller than lambda. So this is a subcomplex of the whole complex. For lambda equals, well, some real number, what we get is just some subcomplex. For lambda equals infinity, we recover the entire complex. And like we said before, I'm so sorry. The cohomology of this entire complex is, sorry, again, yes, thank you, recovers the quantum cohomology. Therefore, we can define the famous spectral numbers, sigma, sometimes denoted by a C, sometimes denoted by a rho, sometimes denoted by anything, really, whatever letters available. In my case, the one available is sigma. That attaches to any cohomology class a number. It depends on the function we chose before because the function determines the filtration. But what we take is the smallest lambda basically, such that the class in quantum cohomology lives in that level. So basically what would be the level of A according to the action of that. What's good about these numbers is that they come from a geometric construction, and therefore they carry geometric information. And okay, this can go really wrong. It can be worse than it already is. They come from geometry. Well, right. So we constructed them from. Yeah. Okay. Never mind. Sorry. We take any cohomology class, we attach a number. These numbers come from some Morse theory, basically, kind of construction. So they carry some information about the cohomology, about functions, about all sorts of things, and therefore they can be also used to prove all sorts of results. For example, and yes, I know this looks horrible. It looks even more horrible than I intended it to be. But if you feel like screaming, that's fully justified. It was meant to be intimidating, even without the extra horror that's going on. Point is, there are concrete and varied applications to these numbers that come from the fact that these numbers are geometric. They satisfy all sorts of relations, and I'm not going to go into this. What I do want you to take away from what we said so far is the procedure. The general procedure was you started with a functional on a loop space. That functional generated a filtered family of chain complexes. The full complex recovered the quantum cohomology. The filtration allowed us to define spectral numbers. Now we can play the same game, but with a twist. For example, we could change a little bit of the first step of the procedure, see what happens. So let's take a branching submanifold. So again, it's a submanifold with half a dimension that has a property. And let's take the same functional we had before, but instead of applying it to loops, let's apply it to paths with boundary conditions in that submanifold. So you can play again the same Morse theory kind of story and get, again, a filtered family of chain complexes. You can even figure out what your product should look like, is if you take two paths, you want to take, well, half of the parapens, because you take boundary conditions in L and L, and see where the other sort of third leg goes. And that the locus of these paths will be the output of the product. Again, if your function happens to be constant, the paths will be also constant, and the product suddenly looks like half of a sphere, aka a disk. This hopefully can give you an idea for, well, what maybe the quantum product should look like. So the Lagrangian quantum product is we take, again, chainless on L, and we, in order to compute their product, we consider all the disks that intersect these chains, see where else this disk can go. The locus gives you the output of the Lagrangian quantum product. And indeed, as hopefully is not shocking by now, we do get an isomorphism between that filtered, between that Morse style cohomology and the quantum Lagrangian cohomology, and therefore we can also, if we will, talk about related spectral numbers. Last but not least is the relative picture. There exists a notion of relative quantum cohomology. I will not give a picture for this because it's maybe a little bit much, but okay. Let's break this down. The relative quantum cohomology comes with a module structure over the absolute quantum cohomology. So we have a map from the absolute times relative into the relative. Mem is the name of the map. You can ignore it, it's fine. What I do want you to know about this map, that it is a lift of the standard quantum cohomology that we talked about, the closed quantum cohomology. So there's a projection from the relative to the closed, and this projection sort of lifts the quantum product to this, except this relative one also incorporates information from the Lagrangian submanifold. And so it looks like a quantum cohomology. I didn't give you the picture, but if you see it, you would hopefully agree. At least you see that it's related to quantum cohomology. To me, it looks like a quantum cohomology. It quacks like a quantum cohomology. I wanted to have spectral numbers like a quantum cohomology. Moreover, I want to know how these numbers relate to the already familiar numbers on the closed and the open Lagrangian theories. And perhaps most importantly, I would really, really like to know if these numbers recover any new information that's not already encoded in what we have. Yeah, so I do hope that my year here is going to be less messy than this presentation was. Thank you for your attention and your patience.
Any questions? Let me briefly ask something. Why did the topology of the loop space not show up in what view?
What topology of the loop space?
It seemed you looked at the space of loops equipped with a null homotopy, and you had some kind of Morse function on that.
Right.
So why does its topology?
So it kind of does, I guess, in the sense that, okay, so we only take contractible loops. So intuitively, I guess people think of it as like the middle dimension cohomology of the loop space, which is supposed to be, which it is this, it's not exactly a Morse function, but it's a floor theory, and it does have to do with the cohomology of the subspace of loops that are contractible. Which is kind of magic that it all sort of fits anyway.
Yeah, Akshay, this topology of the loop space shows up if you study cotangent bundles. Then the symplectic geometry of cotangent bundles is actually pretty much correlated with the topology of the loop space. Now, if you have a compact symplectic manifold, it's more connected with, when you write a Fourier series, it's connected with the loop space associated to the loops which can be represented by positive Fourier series. So it's not really that well understood yet. In which way certain parts of the loop space actually enter. So that's still something under investigation.
Any other questions? Okay, let's thank the speaker again.